So these ones are listed here. This image is exactly the same as what's on the inside cover of your textbook. Okay, so that I like this one because it actually shows the metals and the metalloids and the non-metals. It shows them differently. Notice that all of the blue, those are all the metals. So there's a whole lot more metals than there are non-metals. The yellow are the non-metals. We talked about characteristics of metals versus non-metals. Then those green ones down the middle, not very many of them, but those ones they call metalloids. They actually have some metal characteristics and some non-metal characteristics. So they fall right along the zigzag line, which is the reason that I use the handout that I gave you. And you will always have this. So you don't have to memorize like atomic numbers. You don't have to memorize atomic masses. But the one thing you do need to be able to do is link the name and the symbol. So work on the ones, the 30 that I gave you, 1 through 20. And those are by the numbers on top of above each of the symbols, the first 20 elements in the list, and then add these 10 as well, because we're going to talk about them more and more as the semester goes on. Now, in terms of us, keep going. There are the elements that are found in the human body. 96% of the elements that are found in living things are made up of just 4. So you have carbon, hydrogen, oxygen, and nitrogen. And they call those either the major elements or the main elements. Found in living things, 96%. So in your body, this is what makes up water, H2O. This is what makes up carbohydrates. Carbon, hydrogen, and oxygen is what's found in carbohydrates. This is what makes up fats. Fats are mostly just carbon and hydrogen. And this is what makes up proteins. Proteins actually have carbon, hydrogen, oxygen, and nitrogen. So these 4 elements are the main components that you find in what are known as the biomolecules or the biological molecules that make up the body. So then there are smaller, they call them minor elements. Minor elements are found in collectively up to 3.9% in living things. There's 9 of them. So they are sodium, Na, magnesium, Mg, potassium, remember, is K, calcium is Ca, chlorine is Cl. So those are the 5 that they've got listed. But in addition to these, we also have S, which is sulfur, P, phosphorus, okay? You can see these ones here. So they colored these, and there's 7, not 9. I was thinking of iron and iodine, but they actually throw those in the next list, so we'll just leave them there. But the 7 that they've got are kind of orangey in color. I said these are 3.9%. These are 96%. The main elements and the minor elements, but you still need extremely small amounts of another group of them. They call these often the trace elements. The trace elements, some of them are listed here in purple. Trace elements all together make up about 0.1%, so not very much. And most of them, you find them in very specific places. So they're not just randomly distributed throughout the body. They're found within specific areas. For example, Fe. Fe is iron. And where do you find it? In red blood cells. So you don't find it scattered throughout everywhere. It's found in a red blood cell. So it has a very specific function of helping to carry oxygen in a red blood cell. Same thing, iodine. Where do you find iodine? There's only one gland in the body that uses iodine, the thyroid. So you won't find it circulating or found in other tissues. It ends up getting sort of like sequestered or collected in the thyroid. Some of them, like zinc and selenium. Have you ever taken anything that had zinc and selenium added?
Well, all fish has.
Okay, but why? You can actually, sometimes you'll find that they'll have zinc and selenium added to orange juice.
Oh, so it's fortified.
So why? Why would you want to drink orange juice with zinc and selenium?
Colds.
It's when you have a cold, okay? Because zinc and selenium have actually been shown to improve immune response. So when you have a cold, you take this additional supplement of zinc and selenium to get your white blood cells moving, to get them more activated. So they are used more by immune cells. And so it can help you in fighting off the cold, recovering from the cold faster.
So if you were taking a multivitamin, zinc and selenium every day, it would already have an improved effect.
Correct.
Okay.
But oftentimes people, when they're sick, will actually up those two because they make your white blood cells more responsive.
There's some of that.
Yep. So it's really to try and like promote immune cell response. Okay, so that's really the difference with trace. You don't just find them in every single cell. You're not going to find them scattered throughout the body. Oftentimes they have a really specific function, which is why you don't need very much. So that's why they're found at very low levels. So this leads us into the measurement aspect. So understanding about elements and compounds and mixtures, great. But when we talk about them, we want to talk about how much or about the space that they take up. And so we're going to use what is known as the metric system as the way of counting. So if you're under 30, really you've had the metric system introduced all along the way. So it shouldn't be something that you're like, I've never heard that before. When you're over 30, sometimes you will find that depending on what high school you went to, they may not have talked about it as much. You may not have been sort of immersed in it as quickly. And so it still may be a little bit sketchy or a little confusing. In fact, the metric system is so much easier than the English units, what we use commonly in the United States. In fact, all other countries except for the US and Australia is one that like there's some minor countries that don't use the metric system. And the reason that they've adopted this is because everything can change by just moving decimal places. So you don't have to remember all of these numbers to convert from one value to another. So in metric, there is what's known as a base unit. A base unit is just a single abbreviation for the unit. When you're talking about mass, the base unit is grams. When you're talking about volume, the base unit is liters. When you're talking about length, the base unit is meters. So to give you an idea of a size of a gram, so 1 gram of table salt is just under 1/8 of a teaspoon. So it's literally just bigger than a pinch. So a gram's a pretty small amount. So a gram is like just a small pinch, a couple shakes of your salt, that's a gram right there. A liter, though, that's unfortunately the one that people are the most common or most familiar with. Why? Because what's packaged? Because of soda. So soda was packaged in 2-liter bottles, so people are like, oh, I know what a liter is. Okay? In fact, you find now almost all of your water bottles, they come in 500 milliliter bottles. So this is a half of a liter. So 2 of these would make up a liter. Think of the 2-liter soda, half of those. That's to just kind of give you an idea about volume size. Meter is one, when people talk about running a 5K, that's a 5 kilometer. A meter is just over 3 inches longer than a yard. So everybody knows a yard's about 36 inches. So a meter is about 39 point something inches long. So I always think of meter as being equivalent or very close to what a yard would be. So grams, really small, like a pinch, okay? A couple shakes of salt. Liters, more common volume for us. And then for meters, it's just over the length of a yard. But now when we're talking about English, if you know what a yard is, how do you know what an inch is? What do you have to do to go from yards to inches? Yeah, you have to know that there's 36 inches in a yard, or you have to take a yard and you have to go to feet, and from feet you can go to inches. So you actually have to remember these numbers, these random numbers. And in fact, the random numbers, the foot was the average length of a man's foot. That's how they came up with a foot. So the people that were making shoes, and that became the foot. And a yard became the normal pace. So when you take one step, that became the yard. So you could pace off land by walking it. And that's how many yards. So if you walk 20 paces, that's 20 yards. So they came up with all these random measurements, but then you have to remember what all of those are equal to. You have to remember all of those number values, that there's 3 feet in a yard, that there's 12 inches in a foot, that you have to remember that there's 1,860 yards in a mile. So like all of these numbers that they came to, metric doesn't do any of that. Okay? Metric says everything is relative to the base unit, and it's all changing by factors of 10. So you can add what's called a prefix. So a prefix goes in front of the base unit, and the prefix indicates how much larger or smaller it is than the base unit by a factor of 10. No more do you have to remember to divide or multiply by 36, or if you have to do 12 or whatever those numbers are. So in this, there's really 6 of them that we are going to use. Well, really 5, sorry. There's really just 5 plus the base unit that you really need to commit to memory. These prefixes are kilo, and for kilo, you just put a K in front of the base unit. The term kilo means that it is 1,000 times larger. So it takes 1,000 base units to make 1 kilo. So 1,000 base units is 1 kilo of anything. But this is nice because you can use this for mass, for length, and for volume. So you can have 1 kilometer. 1 kilometer is 1,000 meters. You can have 1 kiloliter. 1 kiloliter is 1,000 liters. It takes 1,000 base units to make a kilo of anything. 1 kilogram is 1,000 grams. So this is a unit value. So really, a kilometer is about 0.6 miles. Okay, so it's just under half a mile. So kilo means it's a big value, a large measurement compared to the base unit of just the meter. So it takes 1,000 base units to make a kilo of anything. All of the other 4, they're all smaller. So kilo's the one you've got to remember that it's actually a larger measurement. All of these other ones are going to be smaller. That's deci, centi, milli, and micro. So deci, D-E-C-I, is a little d. If you put a little d in front of a base unit, that becomes a deci value of the base unit. Deci, I always think of a decimal place. If you move a decimal 1 place, that's 10. Okay, so deci, I think of meaning 10. It is a measure that is 10 times smaller than the base unit. Whenever you see deci, 10 goes in front of it. So if I have a decimeter, it takes 10 decimeters to make 1 meter. Ten decigrams to make 1 gram. 10 deciliters to make 1 liter. So deci means it's 1/10 of that base unit, or it takes 10 of them in order to make the base unit. Centi is 100. So I always think of a century, which is 100 years, or you can think about how many pennies in a dollar, because a cent is 1 penny. It takes 100 pennies to make the dollar. So when you see cent or centi, that means that it is 100 times smaller. They use a little c. It's 100 times smaller. So whenever you see centi, you're going to put 100 in front of it when doing any type of conversion. It takes 100 centimeters to make 1 meter. 100 centigrams is 1 gram. 100 centiliters is 1 liter. A 100 centi makes a base unit. So it doesn't matter if you're talking about mass, volume, or length. Still, you can use the exact same value. Instead of having to remember how many ounces in a pound, instead of having to remember how many inches in a foot, instead of trying to remember how many cups in a pint, instead of trying to remember all of that with English, which you have to deal with all the time, you really just can use this, and it stands for all of them. So the same prefix values are work for all of the different ways of measuring in metric. Milli. So milli is a little m. I think of the millennium, that's 1,000 years. Okay, so the milli means that it's 1,000 times smaller. Then the base unit. So whenever you have milli, you put 1,000 in front of milli whenever you're converting. 1,000 milli equals a base unit. Doesn't matter if you have grams, meters, or liters. 1,000 milli equals 1 base unit of any type. 1,000 millimeters is 1 meter. 1,000 milliliters is 1 liter. And 1,000 milligrams is 1 gram. So milli gets 1,000 in front of it to create this equivalent value. Notice the difference between milli and kilo. So those are two that people oftentimes mistake or get switched around. So when you see kilo, kilo always gets a 1. So kilo, because it's larger, would get the 1, and the base unit gets the 1,000. So notice here, 1 kilometer is 1,000 meters. But over here, 1,000 millimeters is 1 meter. So since kilo is larger, kilo would get the 1 when you're making a relationship to the base unit. It takes 1,000 base units to make 1 kilo, but it takes 1,000 millis to make 1 base unit. So one is 1,000 times larger, the other one's measuring something 1,000 times smaller in size. And then the last one. So the last one's micro, and they ran out of M's. So instead of another weird M, they use what's known as a Greek symbol called mu. And it looks like a U with a little foot on the front. So that is the Greek symbol mu. Micro, I think of microscopic. Micro is super, super small type of measurement. Micro is 1,000,000 times smaller than a base unit. So you got to add a 1 with 6 zeros. So remember we said a gram is like a couple pinches of salt. If you could take those pinches and break it down into 1,000,000 itty bitty pieces, that would be a microgram. So it takes 1,000,000 itty bitty pieces to put together to make those couple pinches of salt. Super small. I always think of it as microscopic, right? So something's microscopic in size, you have to magnify it in order to be able to see it. You're not going to just be able to look at it and go, oh, here it is. So micro is 1,000,000 times smaller, and you will see this sometimes with medications, because strong medications, medications that cause dramatic effects, may be given to a patient in micrograms. So that is that little U symbol. In fact, there are some, especially a lot of your chemotherapy drugs, they can be given in nanograms. Nanograms is 1,000,000,000th. So that's even 1,000 times smaller than that. So we don't use that quite as much in chemistry just because that's a super small amount. So we stick with these 5. So it takes 1,000,000, 6 zeros. Try to make sure I put 6 zeros. 1,000,000 millimeters to make 1 meter. 1,000,000 milligrams to equal 1 gram. And 1,000,000, sorry, not milli, that should say micro, sorry. Micrometers, micrograms, and then microliters to make 1 liter. Takes 1,000,000 micro. So the reason that I write them this way is we're really saying that these are equivalent. So when we look like at deci, 10 decimeters is 1 meter. So they're saying the same thing, kind of like you say 12 eggs is a dozen. So you could say get a dozen eggs, or you could say get 12 eggs. You know, you're saying the same thing. Well, same thing here. If I say 10 decimeters, or if I say 1 meter, it's saying the same thing. They're the same unit. It's just a difference in the size of the individual units. So we can put one over the other, or vice versa, because this is the same. So 10 decigrams, 1 gram, they're saying the exact same thing. We can use that. They call them, because they're the same measurement, just with different units, like 12 inches and 1 foot. They're both exactly the same. They're just using different units. They call them equivalents. So everybody agrees that this means exactly the same. 1 gram, 10 decigrams. Deci is 10 times smaller. I need 10 decigrams to make 1 gram. We're going to use that as what's known as a conversion factor. So we can set it up in a math formula to be able to convert from one metric unit to another, and it's never more than 1 or 2 steps. So in the first step, so let's say that you have 75 millimeters, and you want to know how many meters that is. So a common way that people do this is they use a number line. So they remember where they are in a number line, and they just bounce up and down the number line and change the decimal place dependent on it. In chemistry, we will use this sort of format for all of our problem solving. So I will use this with metric. I will also use this when talking about chemical reactions. We will also use this when we go through gas laws, when we talk about solutions and making up dilutions. So getting used to arranging it this way so that you get your units to cancel, you're going to see it all semester. And it really helps to track and make sure that you don't set it up wrong. Because if you set something up and you end up with millimeters and millimeters on top, they're not going to cancel. So it helps you to kind of check your work. It helps to check to make sure you've set it up correctly so that you don't make those types of errors that you sometimes make when you just use a number line. Like if you miss one of the decimal places, you could be off by a factor of 10. But that could be really bad if you're trying to figure out what dosages are for patients. You don't want to be off by a factor of 10 because that could mean that you've overdosed your patient or underdosed your patient by a factor of 10. So this is why we've set it up this way so you can track your units and make sure that they cancel. So in this one, the unit that I'm given is what I start with. So I always call that the given unit. So the given unit here is 75 millimeters. So the goal is to change from millimeters to meters. So the unit I start with always goes on the bottom in the first step. So I would take 75 mm times in a line. So that's always sort of the first thing I do. I write down what I'm given and I put times in a line. Second step is I want to put the unit I'm given on the bottom because that's going to get it to cancel, right? Given unit and given unit will end up canceling when you do math this way. A unit in the numerator, a unit in the denominator, you can cancel them. So that means the unit I'm given, and it doesn't matter what the unit is, whatever unit you start with, that's the given unit. That one's going to go on the bottom. The unit I want to get to, I'm going to call that the desired unit. So that's the unit of my answer. And so in this one, that unit is meters. So the unit that I want is just meters. So now here comes remembering what kilo, deci, centi, milli, and micro mean. You really only have to memorize those 5 things. Anytime you see milli in this, milli means what? The millennium. So it means 1,000. Every time you see milli, 1,000 goes in front of it and the base unit gets a 1. It takes 1,000 millimeters to make 1 meter. So whenever you see milli, 1,000 goes in front of it. So this is saying the same. This is an equivalent. 1 meter and 1,000 millimeters are exactly the same amount, just with different units, but that's going to allow these to cancel. So to find your answer, which we now only have meters, you take everything across the top gets multiplied, anything on the bottom is going to be divided. So 75 times 1 75. Anything times 1, you can ignore the 1. Remember that 1 doesn't change your number. So you just take 75, divide it by 1,000. So 75, anybody need calculators? I brought them. So 75 divided by 1,000. So decimal places, anybody wants to grab a calculator? I brought some. Gives you 0.075. Decimal place goes to the left by the number of zeros in 1,000. So if you're doing a problem and you have millimeters and meters, or you have deciliters and liters, or if you have grams and kilograms, you can do this. It's the exact same setup. So like with this one, so 24 milliliters is how many liters? So the first step that you do, this remember is the given unit. You're going to write your given unit down, times in a line. So you're going to use a equivalent unit to convert from milliliters to liters. So what unit goes on the bottom? Milliliters goes on the bottom. The unit you want is liters. It goes on top. Anytime you see milli, put 1,000 in front of it. So if milli is your prefix, 1,000 goes in front of it. That means there's 1,000 milliliters in 1 liter. Units will cancel. Everything across the top, divide by each thing in the bottom. 24 divided by 1,000. 0.024. Try the next one. Same thing. With all of them, you always write the given unit first, then put times in a line. Put your given unit on the bottom, underneath the line. Put the desired unit on the top. Figure out what the ratio is. So whichever one has a prefix, you've got to figure out what's the equivalent between my given unit and my desired unit. That'll allow the units to cancel. Then you just have to do the math. So I have listed up here, if you see deci, you put a 10 in front of deci. If you see centi, you put 100 in front of centi. If you have milli, it gets 1,000 in front of it, and micro gets 1,000,000, a 1 with 6 zeros. So if you see any of those 4 because they're smaller, that's what goes in front of that prefix. Kilo is the one that's different. So kilo is bigger. So kilo gets a 1, and the base unit gets 1,000. So it takes 1,000 base units to make 1 kilo because kilo is a large size unit. So that's the only one to kind of put as your, like, it's the oddball in all of this. Kilo is the larger unit. So kilo gets a 1, and it takes 1,000 base units to make a kilo of anything, whether it's deci, if it's grams, liters, or meters. So in this one, 97.1 grams times in my line. Unit on the bottom, grams. Unit on the top, kilograms. Now this, when you see kilo, you go, oh, kilo gets a 1. Okay? With all the other ones, the prefix unit gets a number, but with this, kilo gets the 1, and it takes 1,000 base units to make the kilo. So you see that grams and grams will cancel. 97.1 divided by 1,000. And don't round. When you're doing a unit conversion, don't round. You're keeping the numbers and you're just converting it to another number. So if you've got that, you can do what's known as the two-step conversion. And this is just when you have two prefixed units. So in this one, I have decigrams. So I have deci, remember that's 10. And I have milligrams, and you remember milli is 1,000. So instead of going directly from one to the other, what I want you to do is I want you to do it in two steps. I want you to go from decigrams to grams, because that's a single step. Then go from grams to milligrams, and that's the second step. So in this one, I'm not a fan of the red. First, put down the unit you're given, times in a line, same as all of them. So on the bottom you put decigrams. We're going to do this arrow first. So I'm going to put grams on top in the first step, decigrams on the bottom. Whenever you see deci, you put a 10 in front of it. Takes 10 decis to make 1 gram. So notice that this is going to cancel decigrams, and it's going to leave me with the unit in grams. So I did this first step, but I'm not actually done. I need to make sure that I do the second step. So the second step here, I want to now go from grams to milligrams. So I'm going to do one more, times and a line. What unit do I put on the bottom in this one? Grams. Grams goes on the bottom. That's the one that we have in this first step. That now goes on the bottom, and what goes on top? Milligrams. When you see milli, what do you put in front of it? 1,000. Milli gets 1,000. The base unit gets the 1. Grams and grams will cancel. So now all I have to do is the math, because the only unit I have left is milligrams, and that's the unit that I want. So the math, what do you have to do? So the top 4 times 1,000. Remember that you can ignore the 1, because anything times 1 doesn't change. So it's really just 4 times 1,000. So that'd be 4,000, and divide it by 10. Exactly.
So 4 decigrams is 400.
So if you do it this way, it's never more than 2 steps. You can convert anything. You can convert any mass, volume, or length just using this exact same process. So it doesn't really matter what your prefixes are. You're going to start from 1, you're going to go to a base unit, and then you're going to go to your answer. So in this one, we've got millimeters, and then we have centimeters. So instead of going direct, we're going to do 2 steps, because I have a prefix here and a prefix here. So I'm going to do 2 steps. I'm going to go millimeters to meters, the base unit. And then from meters, I can go to centimeters, which is the unit that I want in my answer. Write down the number you start with. MM times in a line. Right? So it's always what you start with times in your line. I want to do this one first. So I'm going to put millimeters on the bottom, meters on top. The unit I start with is millimeters, so it's going to go on the bottom. Always the given unit goes on the bottom in the first step. And in this one, because I have milli and I have centi, I need to do it in 2 steps and put the base unit in between. Whenever you see milli, 1,000 will go in front of it. Whenever you see centi, 100 goes in front of it. Deci gets the 10, micro gets 1,000,000. It's just kilo that's the oddball. Milli and milli will cancel. So I've done the first step. Then I want to do this step. Meters on the bottom, centimeters on top. So the unit that I get in the middle is going to go on the bottom in the second step. And the answer I want goes on the top. Whenever you see centi, what goes in front? 10. Centi is 100. Think of the century. And if you just need to commit those 5 number values to memory, so that whenever you see deci, you think 10. Whenever you see centi, you think 100. Milli, 1,000. Micro, 1,000,000. And when you think kilo, remember that's 1,000 times larger. Okay, so kilo will always get the 1, and the base unit will get the 1,000. So this and this will cancel. 8.068 times 100 and then divide it by 1,000. 0.8068. So for these two, there is a base unit in one of those units. So the top one, we have liters. The second one, we have grams. If you have a base unit as one of your units, you just do it in one step. So notice with those, we only had to do 1 times in a line. But if you have 2 prefix units like deci and milli, like milli and centi, then you're going to set it up in 2. Go to the base unit in between. So here's where you get to work and talk, setting them up. I gave you the single one and I gave you the double one. Just do the first 2 and then we'll talk about them. If you've got, set them up. Even if you don't have the calculator to do the math, set them up. Compare with the person that's next to you. Couple minutes to work on that. Kim Williams didn't come in. Yeah, I know. I thought that's what I was thinking. I was like, saw her too.
She may be adjusting her work schedule.
Still.
Yeah.
If you see her, tell her that this will be posted tonight, so she'll have an option of looking at it. All right, is the first one step or 2? 2, because I have kilo and I have deci. So that's a 2-step process. So where am I going to go in the middle? Go to liters. So I'm going to go from kiloliters to liters. Then I'm going to go from liters to deciliters. Okay, so everything then is just in relationship to liters. So in the first one, kiloliters to liters, liters to deciliters. So when I go to set up the first step from kiloliters to liters, what unit on the bottom? Kiloliters on the bottom. Oh, I was trying to stay with purple, sorry. So kiloliters on the bottom, what on top? Liters. So see in this first step, I'm going from kiloliters to liters. Kiloliters goes on the bottom, liters goes on the top. Now when you see kilo gets a 1, and liters gets the 1,000. Right? So remember, kilo is bigger. It takes 1,000 base units to make a kilo of anything. So that's the first step. So now I can do the second step. So in the second step, I need to go from liters, where I'm at now, to deciliters in my answer. So I'm now going to do the second step. So what unit on the bottom? Liters on the bottom, deciliters on top. That's my answer. When you see deci, what goes in front? 10 goes in front of deci. 10 deci makes the base unit, so 10 deciliters makes 1 liter. That will allow liters and liters to cancel. And when you do this, multiply everything across the top. Each thing you're dividing by is just 1, so you just ignore those. 24 times 1,000 times 10. So that would be 24 times 1,000 times 10. Just multiply everything across the top, and then you're just dividing by 1. That's not going to change your answer, so you're done. Second one, same issue. Micrograms, centigrams. 2 prefixed units, I'm just going to do it in 2 steps, and grams is going to be my middle. So I'm going to go to grams first, then I'm going to go to centigrams. So when I do 97,123 micrograms is your given unit, times in a line, what unit on the bottom? So micro on the bottom, grams on the top, the first one. Micro means 1,000,000. pen doesn't like that. So you have to put a 1 with 6 zeros. So anytime you have micro, a million goes in front of it. It takes a million micro to make 1 base unit. But I'm not done because I'm here now. I'm in this middle, but I've got to now go to centigrams. So I need to do times in one more line. Unit on the bottom now, grams. Unit on the top, the unit that you want. When you see centi, what goes in front of it? 100, like the century. Base unit gets the 1. 100 centi makes the base unit. That way grams and grams will cancel. So 97,123 times 100, and then divide it by a million. And you ended up getting 9.7123 centigrams. Okay, so I gave you sort of the plan for the other two, so make sure you practice those ones. So you sometimes can have this as like an application in a medical dosage order. And in here, you really have to make sure that units are equivalent. So you can't take somebody's, like, if the doctor said that I want you to give them 500 milligrams per kilogram, and you know the person's weight in pounds, can you just automatically know that amount? You've got to convert, right? So you've got to take their weight and go from weight in pounds to weights in kilograms. So most medications are given in metric. So when you're thinking about a patient's body weight, you might know what they weigh in pounds, but you're going to have to convert. It's the same thing here. If you know the doctor orders 0.25 milligrams of digoxin, which is a heart medicine, and you have a solution, which means that you have a liquid solution of this medicine, and there's 500 micrograms per milliliter in the volume. So how much do you give? Well, you see that you have milligrams of digoxin and micrograms of digoxin. So that's like saying you have like feet and yards. You've got to convert. They have to be in the same unit in order to get the units to cancel. So in this one, so this is the amount, and this is the concentration. And concentration is always the amount per volume. So you compare the two amounts and you see that the units are not the same. So you're going to have to convert one. You can convert one or you can convert the other. It doesn't matter which one you convert. For me, since milligrams is all by itself, I would convert milligrams, and then I wouldn't have to use, like look at the milliliters in there as well. So I have 0.25 milligrams. What do I want to convert it to? I want to convert it to micrograms. I need those mass amounts to be the same unit in order to know how much I need to give them. Milligrams and micrograms, it's a two-step. If I have milli, that's a prefix. I have micro, that's a prefix. Do it in 2 steps. We're going to go from milligrams to grams and then grams to micrograms. So we're just changing the unit for one of them so that we can multiply them and be able to cancel them. 0.25 milligrams times in the line. Milligrams goes on the bottom, grams goes on the top. We're doing this as our first step here. Milli is 1,000. So in front of milli goes the 1,000, which means the base unit gets the 1. But I'm not done. I've now got to do the second step. In that second step, I'm going to take and put what on the bottom? Grams, the unit that I just made. I've got to now get that to cancel so that I can go to the unit that I want. And the unit you want is micrograms. So micro means a million. Every time you see micro, put a million in the front, the base unit would get the 1. So here, grams and grams will cancel. So that's going to leave you with your unit of micrograms. 0.25 divided by 1,000 times a million. So it's 250 micrograms. Nope. So I got to give. So, well, let's set it up first. So in this one, how much would you give? I want to know what the volume is. So I have amount and I have amount per volume, right? So I have 250 micrograms. That's the amount of medicine. And I know 500 micrograms per milliliter. And you can think of it per 1 milliliter. That is the amount over volume. So I want to know volume. So I'm going to get these units to cancel. So how do you do that? You don't have to you could cross multiply, but think about it in terms of the units. What would I need to do to this unit to make amount in the numerator and amount in the denominator? Flip it. So if I have 250 micrograms times, I say 500 micrograms per mil, but that's the same as saying 1 mil over 500 micrograms. So I put 500 micrograms on the bottom, 1 mil on the top. I've just taken and flipped the unit. So I have volume over amount instead of amount over volume. Still the same as what's in the directions. But then notice micrograms and micrograms cancel. So 250 divided by 500 is 0.5. So that'll tell you the milliliters. So kind of following along with units, getting units to cancel can allow you to figure out dosage calculations. But the big one, always double check and make sure like your dosage amounts, the unit values are the same. They have to be equivalent in order to be able to get them to cancel. So we'll work on more of these over the course of the semester. This is one thing that you get more and more comfortable with as we go through. Now, when you do calculations, you have issues with things like significant figures. So significant figures are the numbers that you get when you take a measurement. So they're measured values. And so if you say that I have 1,864 pennies, that's pretty exact. So I'm thinking you went 1, 2, 3, 4, 5, that you made stacks and you started counting them and you get all the way in, you're like, okay, I have 1,864 pennies. That's an exact number that you measure down to the nearest. Now, these ones I'm saying I'm extremely sure about. So maybe I missed a penny. So maybe it's 1,863 or maybe it's 1,865. Like if I made little stacks and maybe there's one extra penny here or there. But this is considered the estimated number. You have the least amount of sureness about that last value. But all of those are considered significant. They're all considered measured. But what if you said, yeah, well, I have 2,000 pennies. If you have 2,000 pennies, the question comes in, did you look at them and go, yeah, I got about 2,000 pennies? Because I compared it to their pile and it looks pretty close. I think I have more. So maybe you just estimated that too. So maybe you didn't measure all the way down to it. So the number 2,000 is a lot less exact than the number 1,864. So in this, you would say that this is actually the known value and these actually may be estimated. Zeros are notorious for being the estimated number. So you're like, I have $1,000 in the bank. Do you have exactly 1,000.00? No, maybe you have 998 and 73 cents. Maybe you have 1,100 in there. So you don't know the exact amount. An estimate, when you talk about numbers with zeros, they say that there's a certain amount of uncertainty. So uncertainty is the lack of being sure. All numbers 1 through 9 are significant. All numbers 1 through 9 are considered measured. Okay? So there may be that last number that's an estimate, but it is still considered a measured value. So 1 through 9 are always significant figures. The problem comes into play with those blasted zeros. Zeros are the troublemakers. So zeros, they really just hold the size of the number. So a 0 on 200 makes it 2,000. 2 zeros makes it 20,000. So zeros just make a number larger or smaller, indicating size, but they're not necessarily measured values. They might just be part of that estimate number. So leading zeros, like a number like this, zeros out in front with a decimal place, they're never significant. Zeros at the end of a number, if there's no decimal place, they're not significant either. So you don't consider them measured values, you consider them estimated values. Like I said, the 2,000, I have 2,000 pennies, okay? That means like, I think I got about 2,000, but I might have 1,900 and I might have 2,100, but I'm estimating it's pretty close to 2,000. So those zeros tend to be more of the estimate. The only time zeros are significant is if you put them in a number that has a decimal. Zeros at the end, when you have a decimal, indicate that you measured down to that point. So that is considered a measured number. So in that one, 0.001250, which zeros are significant? Just the last one. So the one I'm talking about is here. Zeros in front are never significant. Doesn't matter if there's a decimal where it is, they're not. But in that one, it's called a lagging. So lagging is always at the end. So lagging zeros, they're considered significant if you have a decimal place. And then the other one is...
Ma'am, I'm sorry, just to make sure I understand. With the 0.00125, the lagging zero at the end is significant.
Correct.
And the 0.00 are not significant.
Correct. Okay. Zeros in front, never significant. Because I could say this, that's just 1,000, right? I could put a whole bunch of zeros out in front. They don't mean anything, okay? They're just there. If I put a decimal place, that's just indicating where, like the size of that number, but those are not considered measured values. These are not significant, but if I put a decimal place and those 3 zeros come afterwards, now what? These are considered measured. They're measured zeros, and they are significant. Yeah, and we'll do it. There's a dynamic study module on significant figures, and doing that, it'll really help you get more and more comfortable. So just remember 1 through 9, all numbers 1 through 9, you always count them as a significant number. All zeros in between. So see, like I have 2,001. See, or 12,001. That's a difference between saying I have 12,000 pennies and I have 12,001 pennies. So now that 1 at the end makes those zeros measured. So the in between, they are significant because they're considered just like a 1 and a 9. They have been measured and they were measured at the 0 place. So these ones are always significant, and lagging zeros with the decimal place are always significant. Now, when you do when you do unit conversions, don't round the numbers that you start with and the numbers you end with. They're considered exact numbers, so they just stay. So like if you have to convert from one form to another, we'll talk about rounding, but doing things like unit conversions, that number is considered an exact number, and you don't even consider it when trying to figure out what numbers are significant, because it's an exact. 1,000,000 microliters is 1 liter. So that million, right. So it's an exact number. It's not considered a measured number. But if I start off with like 24.2 liters, that's a measured number. If I want to convert it to milliliters, I'm just going to consider my measured number when I do rounding. I don't consider the unit conversion numbers. So we'll practice that in a minute. Okay? So here's a few. Let's see if it'll go forward. Here. You tell me. Okay? So this is in one of your PowerPoint slides. You tell me how many significant figures. 6. Does everybody see 6? Which one's not significant? The very first. So these are significant. There are 6 of them. Leading zeros, never significant. What about 12,500? 3. Which are they? The 125. No decimal place. Lagging zeros, not significant if there's no decimal. What about the next one? 8. because the zeros are in between. Doesn't really matter about the decimal place. If you have zeros in between non-zeros, they're always significant. 0.0025896 decigrams. There's 5. These 5, the non-zero numbers. Leading zeros are never significant. 0.0045100. Which zeros? The 2 at the end. Okay, there's a decimal place, so those lagging zeros are significant. A million, decimal place. So if it was just a million, it would only be the 1. But I have a decimal place. So when you put a decimal, all of your lagging zeros, that's all of the zeros at the end, are significant. So this one is 7. So that means I measured all the way down exactly to 1,000,000 millimeters. Like I measured that. I'm not estimating it, I actually measured it. And on the tape measure, it's exactly at that spot. 9,500.120 decigrams. 7. The zero's in the middle, but you got a decimal place, so any zeros at the end are significant. It doesn't matter if the zeros are in front of the decimal place or the zeros are behind the decimal place. All of the ending zeros are considered significant if there's a decimal place. So not terrible, so maybe that helps a little bit. So how do you use this? So this really comes into play when you do multiplication and division. So if you have 2 numbers and you multiply them and you come up with a number on your calculator that's like 10 units long, how do you know what the number should be? Okay, so for example, so if I take 12.6 times 0.1834, the number I get is 2.31084. So I just keep them all? No. So, and sometimes I'll have it come out and it'll be like the entire thing. You know, it's like 1, 2, 1, 2, 1, 2 repeating. So you end up, you're like, oh, there's a lot of digits here. How do I know which ones to use? The rule is you round to the least number of significant figures in each part of the problem. So 12.6 has how many? There's 3 significant figures in 12.6. 0.1834 has 4 significant figures. So if one has 3 and one has 4, I'm going to have to round to what? To this one. So when you figure out how to round, the way that you do this is just start on the left side of the number and just underline the significant figures you find. So in here, 2.31. Those are the first 3 significant figures that I come through. So that means the rest of them have got to go. So the next number is a 0. So what do? You just drop it, right? So anything that's 5, it's under 5, you would drop those numbers off. So these, I just leave them off. My answer would be 2.31. I have 3 significant figures in my number because 12.6 has 3 significant figures in the problem. Multiplication and division work this way. So you have to look and see how many significant figures in each, and then do the math, and then do the rounding. Addition and subtraction don't work this way. Of course not. Addition and subtraction, you will round to the smallest place setting that they all have in common. So if I have 12.3 plus 1.85 plus 0.139, and you add all those together, what is the decimal place they all have in common? The 1 decimal place. So notice that all of them, the 3, the 8, and the 1 right here, that's the one they all have in common. That's what I got to round to. So you first do the math, 12.3 plus 1.85 plus 0.139. Get that number. 14.289 is that number. But I can't keep all of those because 12.3 only has 1 decimal place. And that 10th is the one they all have in common. So I'm going to keep here. But that means now the next number is an 8. What is that going to do? It's going to round up. Okay? So the number after the point of rounding, if it's 5 or greater, you round up. If it's under 5, it drops off. So this is 14.3. So addition and subtraction doesn't really care about significant figures, but multiplication and division does. So here's another practice. So first, you tell me how many significant figures. So 0.120, 3. 2.782, 4. 12,500, 3. 3.7, 2. Anybody not sure about any of them, just like throw your hand up. Okay? 456.025, 6. Zeros in the middle are 2.30, 3. Does everybody see 3, not 2? Because remember, a decimal place, the lagging zeros or zeros at the end are significant. 19.2544, 6. Any non-zero numbers are always significant, so those ones are always easy. It's just the zeros that are a pain. 25.896, 5. 15.7896, 6. 0.0045100. I had a good time making these ones up. I was just sitting there, like, making up numbers on my keypad. Okay, what about 0.00256? 3. Anybody have any questions about those? Okay, I just want to make sure that you understand leading zeros, never significant. Lagging zeros, not significant if there's no decimal. Lagging zeros are significant if there's a decimal place, and zeros in between are always significant. Okay, so what is this 1 million decimal place? 7. 12.56, 4. 9,500.120, 7. 3.6, 2. 152.1, 4. Good. Okay, so hopefully that's like a refresher, and now you're like, oh yeah, I remember these now. Okay, so the first one, do the math. 0.12, and if you need a calculator, I have lots of calculators. You can use your phone if you need to. 2.782. So I got 0.00, no, that's not what I got. 0.33384. Can I keep all of those? No. What do I have to round to? How many significant figures do I have to round to? Because of this one. Okay? You're going to round in multiplication and division. You round to the fewest number of significant figures in the problem. So 3 is going to be the govern. So when I go across, do I count this 0 as a significant figure? No. So I keep going. So the 3, and the 3. There's my 3 significant figures. So the next is an 8. What's that going to do? Round up or down? Round up. So that 8 is going to change my 4, or 3 to a 4. And you just drop the rest of it off. So there's 3 significant figures in my answer. 12,500 divided by 3.7. And I got a number that's like the entire length of the screen. So 33,378.378, 378. I bet it's 378 repeating. Okay, so that means it would just keep going on and on, 0.378, 0.378. You can't keep all of them. How many are you going to keep? 2. Okay, here's the govern. So now, start again. Start all the way off at the far left and come across. So here's my first two significant figures I see are the 3 and the 3. So that means that there. Next one's a 7. What's it going to do? So it's going to round that to a 4. So what's my answer? 3,400. No decimal. So size-wise, why do I have to put those zeros at the end? Because it's the size of the number. I can't round this to 34. Would you like to have $3,378? And the person's like, well, I rounded. Here's $34. You'd be like, what? I was robbed. That's why. So if there is a decimal place, you do have to keep it to indicate the size of the number. So 3,400 would be correct, 2 significant figures, but we put those zeros on the end to indicate the size. So how's this next one different? Yes, we did all of the significant figures, but does it matter? No. So just do the math. Always do the math. Don't round this first. And again, I got 477.5794. Compare, what's the smallest decimal place they all have? 2. Okay, so notice this one's 3, this one's 2, this one's 4. So here's the one that's going to be the controller. So now I just go 2 decimal places and make a line. So I'm going to have to round everything after that. What's that going to do? Round up or down? Up. So that's going to make this one an 8. So 477.58. Keeping the decimal place, keeping all those numbers out in front. I just have to round the hundredth. Same with this one, 25.896 minus 15.7896. 10.1064. Can I keep all of them? What do I have to round to? 3 decimal places. So see, the first one's 3 decimal places, second one is 4. So it's the one they have in common. So I'm going to keep the 10, the 106, but I'm going to have to round that last one. And so what happens? Just drop it off. Okay, so this would just round off. So if it's a 5 or greater, round up. If it's less than a 5, you round down. Okay, we don't do that odd even thing. If it's a 5 or greater, round up. If it's less than 5, you round down. So 10.106. Okay, so practice those other ones as well. There's those rules for rounding. If you're doing multiple steps, don't round till you get to the end. And really, this is one of the reasons to try and set up a math problem so that you do everything in one step. So you can put all of your numbers in at one time, and then all you have to do is worry about rounding at the end. So we'll practice that as we go through to get you a little more comfortable with it. The last thing that's in this math stuff is scientific notation. So in scientific notation is really a way of trying to simplify what you're looking at. Because when we're talking about the size of grams and the little teeny tiny amounts, we would say that one molecule, like if you took a molecule of water, it is going to weigh 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 21 grams. That's how small molecules are. So they're so very small. You end up with all those zeros. But if you have like a tablespoon of water, it'll be 1 tablespoon of water. That can actually have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 molecules. Yeah. So can you imagine early chemists when they're like, well, let's figure out how big these things are. And they're like, I got all these darn zeros over here. Okay. So this is where they went to scientific notation. So scientific notation takes these humongous numbers or these extremely small numbers and it shortens it so that it's easier to write. So it is always C. C is always a number between 1 and 9 times 10 to the exponent. And the exponent is the number of decimal places you would have to move to make your number between 1 and 9. So we'll just start off with one that's kind of simple. So what about if you have this? So that's this 120 million. If I want to put 120 million into scientific notation, I want to make my number between 1 and 9. So that means that I have to take and move my decimal place 1, 2, 3, 4, 5, 6, 7, 8. I have to move it 8 places. So it would be 1.2 times 10 to the 8th. That 8 tells you the number of decimal places. When 8 is a positive number, you know it's a number larger than 1. If I have 0.00000000023, to put this in scientific notation, you start where the decimal place is. If you don't see a decimal place, it means the decimal place is at the end. Like that number, like that 120 million. But if I see a decimal place, that's the point I start from, and I've got to count the number of zeros, or the number of decimal places I have to move to make this 2.3. Okay, so you start off here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this is 2.3 times 10 to the negative 13. Okay, so if I'm making the number, if it's a number smaller than 1 and it's really, really small, the exponents will always be a negative. If I'm making a number that's a lot larger than 1, the exponent's always going to be positive. So here I want to show you a trick, and then we're going to quit. On these calculators and on yours, you have a special button, a button that math teachers don't talk about, and I don't really know why. Okay, look on your calculator, and if you don't have a calculator, okay, look on this calculator. Look for a button that is a capital E, capital E. It's EE. It looks like this. EE. And then like 90% of calculators have this. This button means times 10 to the in one thing and doesn't require parentheses. It's like a magical button. So you see it? Do you see? And on these calculators, these ones are the bomb because EE is a major button. Okay, so you see the EE? Do you have an EE? That's it. Okay. Do you see one? Do you see an EE on yours? All right. So I want you to put in 1.2 EE4 and hit equals. Nope. When you hit the EE, it'll say E.
I did it, right? And then
have to look at it. I'm trying to think on yours, like how it actually does it. But what it does is it's a way so that, like, if you use this, it also automatically brackets your exponent. So you know when you multiply two exponents or divide two exponents, when you do it in your graphing calculator, you do the parentheses stuff. If you use this, it actually puts the exponents all in brackets. So you can just multiply them directly. You don't have to worry with the bracket part or parentheses. Like you have to make sure that you parentheses those values or else they won't get multiplied correctly. So practice the dynamic study module and the significant figure. The dynamic study modules for exponents and for significant figures, that is in MyLabs Plus. So now the note for next Monday. So Monday we do not have class. It's Martin Luther King Day. What I will do is I'm going to post a video and you can see that I have, let's see if I can find it. You can see that I have here. I have already posted in, not that one, in here for you guys. I posted in the Moodle website in the first exam module. So I posted the lecture that we did last time. That is this, okay? I will post another lecture where I'm going to do more examples of unit conversions, more examples of significant figures, more examples of rounding, and doing more exponents. So you can go through and do those. I'm going to use those handouts. So this page, I'll use this for the unit conversion. So this page, front and back, is nothing but doing unit conversions. So if you're still kind of like, I kind of got it, like you can work on that one, but then watch the video. I'll go through more examples of it. And then I'm going to talk a little bit about like temperature and energy, stuff that's pretty simple, pretty basic, that is covered in chapter 1. So when we come back next Wednesday, we can finish up balancing equations and talk about stuff in chapter 2. Okay, we lose a lecture because of Martin Luther King Day, but this way you guys will stay in sync with the other class. So starting tomorrow afternoon, I'll make sure it's up. Look for this, look for the lecture from today. That one will say chapter 1, it'll say like unit conversion, significant figures, and rounding, but then there'll be another one that I'll post and I'll put that as an out of class lecture review and part of chapter 1, okay? So I'll have review, plus I'll talk a little about what temperature values mean and what energy means, and then that'll pretty much finish up stuff that I need to cover in chapter 1, okay?